Hello and welcome. In this video, I'm going to talk to you about harmonics and resonance, and I'm going to refer to Sardaukar throat singing or overtone singing from Dune Part 1. I recently saw the movie because I want to see Part 2, and when I see Part 2, when I see it in the theater, I'm going to uh, probably make another video, but for now I just want to go through harmonics and resonance very quickly and uh, show to you why these two concepts are important for overtone singing and why these concepts are used for Sardaukar, which is our emperor's army, right? The throat singing in Dune sounds something like this. Apologies, but yeah. And it's very threatening and menacing, and we will see why it sounds like this. First of all, let's start with a simple wave. This is a simple sound wave, a sound wave that repeats itself, right? It means that it's a periodic sound wave in the sense that the cycles are very repetitive. Aperiodic ones are the ones where the cycles are not repetitive, right? And it's a simple sine wave. It has certain components, and the main components of this sound wave are amplitude, which is at 1. You don't have to know about the unit, just 1, number 1, as you can see here. And it has frequency, which means the number of the repetition of the cycles in 1 second. So how often do the cycles repeat in 1 second? And let's draw. This is 0. This is where the sound wave starts. It goes from 0 to the amplitude of 1 to maximum displacement, then it goes back again, then to the minimum displacement, or again maximum but in the other side, and it goes back. So this is 1 cycle. Then we have another cycle and another, and finally a 4th cycle, right? So this is a sine wave with a frequency of 4 cycles per second, or more commonly known as 4 hertz, right? I won't get into that why these are hertz, but they are hertz. Okay, we got that covered. Now, how do we get a complex wave? Well, we have a simple wave, number 1, and we add a simple wave to another simple wave, number 2, and we get a complex wave. This simple wave, number 1, has the amplitude of 1 and frequency of 4. So 1, 2, 3, 4. But this simple wave has the frequency of 12 hertz and the amplitude of 0.5. So it's half the amplitude but 3 times larger frequency. Okay, when we combine these two, we get a complex wave, right? So the complex waves components are the 2 simple waves. That's all you need to know for now, right? This is important because I'm going to enter the slideshow, because of Joseph Fourier. Joseph Fourier, I guess that's how you will read it, was a French mathematician who studied heat and periodic motion. His idea was that any complex periodic wave can be constructed out of a combination of different simple waves, right? Just like we did. And the simple wave components of a complex periodic wave are called harmonics. Harmonics are basically simple waves because they have those components that create or that make up one complex wave. The analogy is light. If you have white light through glass prism, it will break into infinite shades of colors, right? If you like Pink Floyd, you might like this analogy as well. So we have two perspectives, a waveform, which is what it looks like. It looks like this: amplitude in time plus frequency, whereby we have one simple waveform plus another waveform, we receive a complex waveform. We can represent this in another way with a power spectrum. A power spectrum shows on the y-axis amplitude and on the x-axis frequency. It doesn't show time component. And in this case, as you can see from the first one, the power spectrum shows that the frequency of this one is 4 and the frequency of this one is 12, while the amplitude is 1 of the first one and 0.5 of the second one, whereby we receive two components of the same equation, or two harmonics. So again, I'll show it to you. So we have amplitude on the y-axis here, and we have frequency over there on the x-axis. Imagine that somebody was drawing and that we have 1, 2, 3, and 4. That's what our frequency of the first waveform is, right? And here, if you go 1, 5, 6, 7, 8, 9, 10, 11, 12, that's the frequency of the second waveform. All right. And as you can see, the amplitude is 0.5, while the amplitude here is 1. Okay, we got that covered. This power spectrum is just a different visual representation of what I showed to you a couple of slides ago. Why? Well, I wanted to show you what harmonics would look like. These are essentially the two harmonics of the same complex waveform, right? The component sine waves. Okay, we got it covered. We now know what harmonics are, but what about, and let me actually show you one more thing here. Oh, okay, I maybe leave it for later. Okay, so the second part of the theorem is that the harmonics of any complex periodic wave all have a frequency that is an integer multiple of the fundamental frequency of the complex wave. This means that a harmonic of 100 Hz will be the fundamental frequency, will be the basic harmonic, and each harmonic after that one, or the frequency of the next harmonic, will be the integer multiple, meaning that 100 plus 100 is 200, 100 plus 100 is 300, and so on and so forth. We can go long, go up to an infinite number of harmonics. This is important because we want to know what our fundamental frequency is, or the first harmonic. So fundamental meaning basic, frequency would be the first sine wave, the first component wave of this large complex wave, and a fundamental frequency is annotated as F0, right? And let me show you what I mean by this. So I'm going to create a very complex tone. On the left, I have an amplitude of 1. On the right, I have the amplitude of 0.5. Okay. Now this is a formula for creating a sine wave. 2 times pi times 300 hertz. So the first component wave will be 300 hertz. The second will be 500 hertz, but they will have different amplitude. The first will have an amplitude of 1, and the second will have the amplitude of 0.5. And the end time would be 1 second. So in 1 second, we will see how this complex wave, out of 2 waves, 300 hertz and 500 hertz, will be, oh, balloons, nice, will be there, right? Okay. So let's see what it looks like. As you can see, the representation on up here in the upper part of this Pratt panel is waveform. Let me show it closer. Waveform, right up there, but down there are the component waves. You can see the 2 largely dark bars. The first bar is a component wave number 1. The second bar is the component wave number 2. The first bar is a component wave of the frequency of 300 hertz. The second one is the component wave of the frequency of 500 hertz. And this blue line shows the fundamental frequency, which is 100 hertz. If you think about it, this is what I mentioned earlier. If I have if I have 2 component waves of 300 hertz and 500 hertz, the fundamental frequency has to be 100 hertz, right? Just mathematically calculated. And this is what it looks like. You can see the repetitiveness, but it's still a complex wave, but it's a periodic wave. I'm going to show you, okay, I'm going to do this to spectrum, and okay, maybe it's another, where is it? Oh no, it's here, sorry. Yeah, it's here. And as you can see, this is my power spectrum. The first wave is at 300 hertz, right? I cannot point exactly. Okay, 300, I'm good. And the maximum amplitude, right? 1. The second wave is at 500 hertz and a lower amplitude, 0.5. And these are the 2 waves that make up this one big wave. Okay. All right. Yep. So we got that covered. Now let's move on to harmonics in speech. The trilling of the vocal folds creates complex wave with fundamental frequency, with its first harmonic and then second harmonic and so on and so forth. The complex wave consists of a series of harmonics, right? The spacing between the harmonics depends on the rate at which the vocal folds are vibrating, so on this first frequency. We cannot change the frequencies of the harmonics independently of each other, but we need to change them in order to be able to speak, right? How do we do this? How do we get the spectral changes? Because if we cannot change, okay, this is for example a one complex wave, right? We know a fundamental frequency, or the first harmonic is 100, the second one is 200, the third one is 300, and so on and so forth. But this is no speech. We need something else for speech, right? I can also maybe record, show you something like maybe not so stable, but this is fine. I'll grab maybe this chunk, which you can see it's stable, right? So again, okay. So as you can see, this is a very complex wave, right? Complex wave, but it repeats itself, right? And it has a frequency of 124 hertz. The first harmonic, or the fundamental frequency, my pitch was at 124 hertz. Around that, yes, exactly. Okay, now if my pitch was at 124 hertz, first harmonic, what would be the second harmonic, right? Well, the second harmonic would probably be 124 plus 124, 248, right? Somewhere there, at around 250, right? Okay, then the third, the fourth, and so on and so forth. You can see these bars, each of these bars in the lower part, in the lower part of the screen, each of these bars is showing a single harmonic. All right, very well. But this is still not speech. I need some change. This is just one vowel, which is I don't speak like that. We don't speak like that. We need some changes in speech, right? Some spectral changes. The answer is the resonance. The answer is that we change the intensity of the harmonics. And listen to this. Maybe like this. Okay. It sounds like there are two tones, right? And this is a typical overtone singing, whereby the first harmonic remains the same, and the second and the third and the fourth, you cannot change them, right? Fundamental frequency is there, but what you change is the intensity of the harmonics, loudness, right? And as you can see, if the first harmonic is, let's say, at 60 hertz, the second is 120, and so on and so forth, at some point this person is changing the intensity, right, of 1, 2, 3, 4, 5, and so on and so forth, of some harmonic out there. And I will play it again and go along with my cursor so that you can hear and see how this person is changing the harmonics here, or the intensity of the harmonics. Okay, maybe I went a bit too fast, but you get the sense, right, of how it was changed. How is this done? Well, we can selectively amplify or dampen specific harmonics, meaning amplify and make it louder, in a speech sound by taking advantage of a phenomenon known as resonance. Resonance is when one physical object is set in motion by vibrations of another, right? Generally, a resonating object reinforces sound waves at particular frequencies by vibrating at those frequencies itself in response to the pressure exerted on it by the sound waves, right? So resonance makes sounds at those frequencies louder. So basically, our resonator is our throat and mouth, right? And we are using our vocal folds to make sounds such as ah, eh, ooh, right? What we are doing next is amplifying some harmonics, so to make it different, to make these sounds different, right? How? Well, we are using the resonance. The sound waves are going through our throat, right, into the mouth and exiting our mouth, and we're shaping our mouth in certain ways, moving the tongue in certain ways to make vowels, let's say a, e, I, o, u, I, and so on, right? Different vowels exist in different languages. So resonance is basically the reinforcement of particular frequencies, but making them louder. And yeah, overtone singing is done this way. The fundamental frequency is kept constant, like you can see here in this photo, this blue line, but there is a lot of changes in the intensity. The darker the bar, the more intense or louder these sounds are in the intensity of at specific frequencies. This is a tradition of the people of Tuva in Russian region in Siberia, in the south of Russia, right, towards Mongolia. And overtone singing can be sung with a creaky voice as well. A creaky voice or vocal fry, meaning a voice like this, right? And this is called kargira, right? Or I think that's how it's pronounced. Let's hear out kargira and how this sounds. And so on and so forth, right? Kargira. We come to the Sardaukar. Sardaukar are fierce emperor's warriors. They live on Salus Secundus planet, and this planet is known for its harsh conditions. I assume that because of that description, the singing that was created by David J. Peterson, and I think the language, Sardaukar language, was created by him as well, was overtone singing, because Siberia and that part of the world is known for its fierce conditions, right? So I assume that. And David J. Peterson is famous for the creation of the Dothraki and Valyrian languages and some other languages. He's one of the most famous conlangers out there. He worked on Game of Thrones, right? So he worked on Dune's languages as well. And this is, I think, his rendition of overtone singing for the Dune. Something like that. So the point is that his fundamental frequency remains the same, but so harmonic number one is the same, but using resonance, reinforcement of certain frequency, the intensity of certain frequencies, he manages to do the throat singing or overtone singing. In the end, I hope you like this presentation. If you did, please like and subscribe. I hope you learned something about harmonics and resonance, and please take a look at other videos that I have on phonetics and on linguistics. I have a lot of them. Thank you very much.